All right, welcome back again, everybody. Today we're doing section 16.8, which is all about Stokes theorem. This is kind of rounding out the end of the course, actually. There's only two more sections. There's this section on Stokes theorem, and then there's the next section on the divergence theorem. So we're going to get these two really, really important, really fascinating theorems right at the end of the course. So I hope you're as excited as I am because these things are just phenomenal, phenomenal results. So let me pull up the slides. Here we go. All right. And here's the overview. This lecture will actually probably be pretty short. Stokes theorem is nice. We'll do a couple examples. We're going to prove Stokes theorem, of course, and then at the very end, we're going to clarify circulation. We're going to give circulation a little more of a refined definition, and then we'll talk about curl and conservation at the very, very end here. But this is the overview: development, the statement of Stokes theorem, the proof. We'll do a couple of examples, and then circulation and curl and conservation. So here's the setup. Yeah, put succinctly, Stokes theorem is basically a generalization of Green's theorem to non-planar surfaces. But maybe more accurately, it is more accurate to say that Green's theorem is a special case of Stokes theorem when the surface is a region that's embedded in the xy plane. So the first thing I want you to do is just recall this version of Green's theorem that we saw earlier in this chapter. This is one of the vector forms. There were like two vector forms of Green's theorem. And it basically said that if you wanted to compute this line integral, you could equivalently compute this double integral right here. And Green's theorem was only for planar surfaces, so you can just imagine the region is embedded in the xy plane. That's what's going on here. So Stokes theorem yields a similar result to this one, except this is for non-planar surfaces as well. So you can be out of the xy plane. You can be like a parameterized surface, for example. So here's a little bit more of the setup. Let's say we have a surface S, like so, and we're going to orient it with its outward unit normal vector pointing like so, out, all right? Now, when you choose the orientation of your surface, that actually induces an orientation of the boundary, a positive orientation of the boundary. And this is what this figure is showing right here. I mentioned this earlier on. Man, I forget which section, maybe geez, like section 16.3 or 4. But basically, the idea is this: if you have a positively oriented curve, then if you imagine yourself walking on that curve, your head will be pointing in the direction of the outward unit normal vector, and the region will always be on your left. So for me, that's that, but for you all, it's that way. So your curve is positively oriented if the region is always on the left, if you were to walk around the curve with your head pointed in the direction of the normal vector, the outward unit normal vector. Yeah, that's what this all says. So that's the basic idea. That's a positive oriented boundary. Now here's the statement of Stokes' theorem. It says, let's suppose you have S, which is an oriented piecewise smooth surface that's bounded by a simple, closed, piecewise smooth boundary curve C with positive orientation. We're going to let F be a vector field whose component functions have continuous first partial derivatives. So it's C1. Those component functions are C1. On some open region in R3 that contains the surface S, then when you have all of those situations, you get this, that the path integral over C of F is equivalent to the double integral over S, the surface integral of the curl of F, curl of that vector field. So that's the statement. Couple bits of intuition here. So this is pretty analogous to Green's theorem. So essentially what this is saying is that the circulation, quote unquote, of your vector field F along the curve C is the same as the sum of the curl over the surface S bounded by C. So kind of the same result we had for Green's theorem, right? But now the difference is this is just for a surface S. It doesn't have to be a planar region. What's also really cool about this is why sometimes this is called one of the fundamental theorems of calculus. Notice that this is basically saying that if you want to compute this surface integral over a surface, you can do it by actually evaluating an integral over the boundary of the surface. And that's basically analogous to the fundamental theorem of calculus part 2. It's giving us the criteria and the condition that allows us to compute an integral over a region by just looking at data or information on the boundary of that region. This is the boundary of S right there. So pretty cool stuff. All right. Oh, yeah. So let's see the connection, the explicit connection to Green's theorem. So for a moment here, pretend that your surface S lies in the xy plane and that we give it the usual upward orientation. Then the unit normal vector is just the vector k, right? That's the basis vector in the z direction, right? Or in the k direction. So when we use that as our outward unit normal vector, then Stokes theorem becomes this. This is Stokes theorem right here. But now our outward unit normal vector is k. So this becomes k dA, right? But remember, the curl of f dotted with k is just going to pick out that last component function of the curl vector, which is that. And voila, that is Green's theorem. That's exactly the same thing that Green's theorem says. So the difference here is that this outward unit normal vector may not always be k, but in the case of a planar region, it is k, right? Or maybe negative k if it's oriented downward. But that's the idea. So now we can do this in more generality. Just another quick reminder, it's common to use the symbol partial of S to indicate the boundary of a surface. So Stokes theorem can be rewritten like so. And sometimes this is a little more suggestive. It's basically saying if you want to compute this surface integral, you can compute this path integral over the boundary of S. That's the idea. Okay, let's see the proof. So we are going to go through a complete proof of this. But what we're going to do, just because the proof requires some pretty heavy machinery in general, we're going to prove a special case where the surface is just given as a function of x and y. So a surface that looks a bit like this. Again, it can be proven in generality. You can actually see the proof on the Wikipedia page if you're particularly interested. But just to keep things easy and just to build a little bit of intuition, we're going to do the proof in this case. So first we're going to suppose that our function g is C1, and we're going to suppose that D is a simple planar region whose boundary curve C1 corresponds to the boundary curve of S, C right here. So the picture is the setup in essence. Here's our surface S, and the projection of S onto the xy plane gives you this simple region D. D has a boundary curve C1, and this boundary curve corresponds to the boundary curve of S up here. In other words, the projection of the space curve C onto the xy plane gives you the curve C1, the boundary curve C1. So if the orientation of S is upward, then the positive orientation of our curve C corresponds to the positive orientation of this curve C1 as well. That's our unit normal vector right there. Okay, so let's write our vector field f in this form, pi, qj, rk, where the partial derivatives are continuous, so we're assuming they're C1. Then since S is just a graph of a function of x and y, we can actually apply that formula that we saw in a previous section, 16.7, where we replace f with the curl of f. So I made a little note of it in that section that we were going to reuse it, although I think I said 16.9. We're actually going to use it in both sections, here and then also in 16.9. But you can review that. Oh, geez, I forget what slide it's on. Let me briefly look it up real quick, just so you can kind of compare. Where are you? Where are you? Where are you? Nope, too far, too far. Give me one moment here. I got it. Oh, yeah, okay. It is this one. So maybe, oh no, I don't have it set up yet. But if you look at slide 41 from my lecture on section 16.7, slide 41 has the formula that we're about to use right now. Okay, so that's this formula that you see here. The only difference is in that formula, f is just f, and we're going to treat our vector field as curl of f. Remember, curl of f is also a vector field, so it is valid to do this. And also because our function is just the graph of the function of x and y. So that's what this formula is right here. There we go. Now what we're going to do is we're going to parameterize our boundary curve C1. So we're going to just write a parameterization out. We're going to say that the parameterization is x of t, y of t, and then we're going to let t go between a and b. Then the corresponding parameterization of the curve C, that's the projection onto the xy plane, is given by this, x of t, y of t, and then, oh, sorry, I have it backward. C1 is the projection, my bad. I'll restate that in just a minute. And then the z coordinate is this value right here. So you gotta like, strike that, reverse it for a minute here. Remember, C1 is the parameterization of that curve down here, or C1 is this curve. So how do you parameterize the curve C, the one up here? Well, you basically use the parameterization that you have for X and Y for this curve. And then to get the Z component of the parameterization for S, we just need to pick the points that actually lie on the surface. And that's what's going on right here when you look at this part. So X is that, Y is that, and then Z is our function G evaluated at X and Y. And that'll give us the parameterization of the boundary of the surface. Okay, now it's going to get a little bit technical with some algebra. I encourage you to go through all this on your own. I'll go through some of the details, but I won't dwell on them too long because it's really just a matter of doing the actual operations. So if we look at the line integral in the statement of Stokes' theorem first, we get this. There's that line integral. We're going to write it in terms of t, write our differential in terms of t. And then we already had a structure for f, and now we have a structure for r. That was the parameterization we just derived. So we get this right here. And then now what we're going to do is we have to use the chain rule to get this derivative right here. Because remember, z is a function of x and y. So if we want to compute dz dt, then we need to basically multiply these partials and then add all the paths. So that's the chain rule in action right there. Next, what we're going to do is we're going to move some things around and factor some things out. That's what you get right here. Okay. And then we're going to write everything in terms of these differentials, dx and dy. So notice here with this integrand, our differential is dt, but we can write that equivalently as this integral right here, where the differentials are in terms of dx, or in terms of x and y. And that's what we have right there. Okay. Now, by Green's theorem, we can take this path integral, which we now have the form of this, and we can apply Green's theorem to it. So because remember, this is a planar curve, right? So we can apply Green's theorem to this planar curve, and we get this right here. That's our new integrand, and now we're doing a double integral over the region D, all right? Okay, now this is where things are gonna get a little bit messy, so you may have to pause and look at it and go through the details on your own. But remember that all of P, Q, and R are functions of X, Y, and Z, and Z is a function of X and Y. So we have to use the chain rule if we want to compute all of these partial derivatives right here. In essence, what we want to do is just compute the partial derivative of this with respect to X, and compute the partial derivative of this with respect to Y. But we're going to have to use the chain rule. So this is what you get here. If you want, you can pause and ruminate over where all this is coming from, but it is just a simple application of the chain rule and the product rule. So when you do that, you get a very long integrand. This is all one integrand right here. But then because this term is negative, you get a bit of cancellation. So that's what's happening here. These cancel right here, and then these cancel right here. You can simplify things. And then what I'm doing here, this is after simplification. Then what you do is you just move things around, use commutativity and shuffle things around a little bit like so. And then what you can do is you can factor out all these partial derivatives. So for example, from these two terms, I can factor out partial z partial x. From these, I can factor out partial z partial y. And then this one just stays the way it is like so. All right. But if you look very closely at this, this is the curl of f. So this is the curl of f right here. And we're dotting it with this outward unit normal vector, the one given by this, and then a 1 here. I don't know if you can quite see it. Maybe I'll emphasize it here. This piece, and then there's a 1 right here. And that's the outward unit normal vector for that surface. So if you don't recall that, look back at earlier in the chapter, I forget which section it's in. But that gives us the curl of S, and we're doing this surface integral now. Boom. That's it right there. And that's Stokes' theorem. That was what we wanted to show, that this was equal to this. Pretty cool stuff. Okay, so one of the amazing things about Stokes' theorem is this corollary, and maybe some of you were kind of thinking of it when I first introduced it. Basically, the conclusion of Stokes' theorem is independent of surface. which is really wild. So appropriate surface, the surface has to be quote unquote nice enough. But more specifically, if I said, we could say this, if S1 and S2 are oriented surfaces that have the same oriented boundary curve, then, and they both satisfy the hypotheses of Stokes' theorem, then it doesn't matter which of those surfaces you compute over. So in particular, this is equal to this by Stokes' theorem, but it's also equal to this by Stokes' theorem. So in other words, this is the weird thing, any appropriate surface can be used to determine the circulation of a force field around a closed curve. So it's pretty wild. Like just imagine you've got a space curve, right? Space curve in space. You can use any appropriate surface that has that curve as a boundary in the statement of Stokes' theorem. Any surface you want. Amazing, just amazing. And now you're going to get to practice this, all right? So here's an example, and I do want you to try this on your own. You have the statement of Stokes' theorem, and what we're going to do with this first integral, or this first example is, we're going to use a path integral to evaluate an equivalent surface integral. So basically, you're going to try to compute a surface integral by passing instead to a corresponding path integral that satisfies Stokes' theorem, all right? So here we go. I want you to try to use Stokes' theorem to compute this integral right here, where f is given by this vector field here, and the surface S is the part of the sphere x squared plus y squared plus z squared equals 4 that lies inside the cylinder, given by x squared plus y squared equals 1, and above the xy plane. So let me emphasize a little bit more what's going on. S is this little piece that you see in the picture. It's that little bulbous surface right there at the top. And what I want you to try to do is I want you to try to compute this surface integral by instead using Stokes' theorem and passing to an equivalent path integral, okay? So think about it for just a minute, kind of wrap your head around the problem. Okay, and now say something out loud. Remember, you always got to say something out loud to your friend, to your neighbor, to your parents, your cat, your dog, yourself, your can of sparkly, just something to give your brain that verbal feedback to help you make sense of things. All right, now try to work it out on your own and we will do it together. Remember, you're trying to compute a line integral here, a line integral. Okay, all right, here we go. So let's see, we've got our surface here and we can apply Stokes' theorem to it. We just need to find a parameterization of that curve. Yeah, we need to find a parameterization of this boundary curve that you see in the figure right here. In other words, we need to find where these two surfaces intersect. So this boundary curve is the intersection of those two surfaces. And I know that's something that we've explored a great deal throughout the course. So hopefully this isn't too difficult. Just looking at the equations of our two surfaces, we can pick together what the z coordinate of this curve is going to be. And here's how we do it, right? So where is it? Where is it? Okay, so right here, this cylinder is x squared plus y squared equals 1, right? And that appears right here. So what we can do is we can basically take this and shove it into here, and we get this result instead. Little fudged around, maybe here, maybe I could write it like this. 4 minus z squared. Okay, think about it like this. If I take z squared and I subtract it from 4 right here, then I'm left with x squared plus y squared over here, which is equal to 1. That's how I'm getting this formula right here. Okay, now we can solve for z. So solving for z gives us that z is equal to square root of 3. And we're just going to pick the positive one because we're assuming that we're above the xy plane. So we only need the positive square root. Now, it makes sense if you look at the curve, right? The curve is the intersection of that cylinder and that sphere. So it's not going up or down. That curve, the z coordinate of that curve is always going to be fixed. And it's going to be fixed at this value. It's not like oscillating or anything like that. So that's what the z coordinate is. Then, because it's circular in the x and y directions, we can just use the standard parameterization of the unit circle, cosine t, sine t. And then there's our z coordinate right there. All right, so now we have the vector function for our curve. And now we can proceed. Now we can compute that, that line integral over this curve. So just a reminder, this is our vector field f. This is the vector function for that space curve C. And when we take the derivative, we get this. So that's the derivative of our space curve. Now we can evaluate our vector field on that curve by plugging in the x, y, and z components appropriately up here. So x in this case is cosine t, so that should be cosine, that should be cosine, right there. And then y is sine of t, so that should be sine, that should be sine. There you go. And then z is root 3, so that should be z, or sorry, that should be root 3, that should be root 3, there and there. So now we've got our vector field evaluated on that space curve. Now we're ready to evaluate the line integral. Here we go. So by Stokes' theorem, this surface integral that we wanted to compute is equal to this line integral, which we can now compute using the parameterization we derived and evaluating our vector field on that curve. So this gets rewritten like so. Now we're integrating in terms of t, right? And this becomes a pretty straightforward integral. It's nice. Integrating from 0 to 2 pi, because you go all the way around, right? All the way around the curve. That's what that dot product gives us. Then when we simplify, oh yeah, check this out. You've got cosine t sine t and cosine t sine t. So that's going to be 0. Yeah, can factor out the root 3 from both of these terms. And then you get 0 as your integrand. So this is going to be 0. There we go. In other words, that surface integral is 0. Okay, now let's do another example. So I do want you to try this one on your own as well, but this one we're going to go the opposite direction. So what I want you to do this time is we're going to evaluate a line integral by instead evaluating an equivalent surface integral. So this is a situation where you're not going to do a line integral, you're actually going to do a surface integral, and the surface integral is going to be easier to calculate in some respects. All right, so let's read it, and then I'll let you think about it and let you try it out on your own. So here I want you to evaluate this line integral where the vector field f is given by these component functions, and c is the curve of intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1. And this is what the intersection looks like right here. Okay, so that curve, that's the intersection. Okay, so take a minute and think about how you would do it. And then give your brain some verbal feedback. Say to yourself what you're going to try first. Try that. Right, and now work it out on your own. Remember, you're going to compute a surface integral, so you got to think about how you would compute a surface integral, and then we'll do it together in just a moment. Okay. All right, here we go. Here we go. All right. So, yes, we're going to compute a surface integral. Yeah, we could actually do this line integral directly, but it's actually going to be easier to use Stokes' theorem. So first thing we need to do is compute the curl, right? So we have to compute the curl. Remember, the curl of the vector field can be determined using this little determinant trick, and then it'll give you this. Okay, so we got the curl of f. Now here is the fun part. So you actually have a choice of whatever surface you want to use, as long as that surface has this curve as the boundary. So you could use some wacky surface that looks like this, as long as that surface has that as a boundary. It really doesn't matter. Why you would want to use such a wacky thing, I don't know. So maybe the most appropriate or most natural choice in this case is to use this ellipse that lies in this plane and then has this curve as its boundary. Probably the most natural choice. Even if you think of like soap bubbles, right? So soap, think about what soap would do. What would soap do here? Soap would snap into that flat surface right there. So let's just use that as the surface. So yeah, the ellipse is embedded in this plane and it's bounded by C, like I was just saying. We can project this ellipse onto the XY plane and we're just going to get a circle. Good old unit circle, radius 1, centered at 0. And then next we just need a z component. So the z component is 2 minus y. And so now we can describe that curve C by this vector function. We can actually use x and y as our parameters. So x is x, y is y, and z is 2 minus y. And that's the vector function for that curve right there, the curve C. Okay, now remember, to compute a surface integral, we need to compute an outward unit normal vector. So what we can do is we can compute the cross product of these partial derivatives. That was what we learned in the previous section here. So when you compute the cross product of those partials, I'll leave that to you to do, you get this calculation. So this is, where is it? Where'd you go? Where am I? Sorry, I lost my train of thought. Curl FDS. Oh yeah, there's our outward normal. Yep, yep, yep. Okay. And then where is, oh, that's right, because the unital part already gets taken care of. Now I remember the calculation from previously. For a minute there, I was wondering why we weren't normalizing it, but then I remembered that when you pass to this parameterization, it actually ends up canceling out, remembering the calculation from previously. So walking through it, we get curl of f dot that cross product. Here it is written out component-wise. When you do the dot product, you get a very, very nice integral, very simple integral, right? And because the region D is just the unit circle, it's super easy to parameterize, right? Radius r goes from 0 to 1, theta goes from 0 to 2 pi, dA becomes r dr d theta, just the change of variables formula, right? And now you've got a pretty basic trigonometric integral that you can evaluate in whichever way you feel most comfortable. So we're integrating with respect to r first in this case. So apply FTC2, evaluate at the endpoints and subtract, and then you get this. And then this is another fairly straightforward integral to compute, just a single integral. And then when you go through that application of FTC2 and simplify, you get pi. So there we go. That's it. So Stokes theorem to the rescue. All right, so now what I want to do is talk a little bit more about circulation. So yeah, I talked about this earlier. I mean, I think it was like chapter 6 or section 16.4. But I gave kind of a rough idea of what circulation is. Now we're going to get an explicit definition of circulation, and we're going to see how Stokes theorem connects circulation and the curl of a vector field. So let C be an oriented closed curve, and let V represent a velocity field for now. Now, remember that v dot t is the component of that vector field in the direction of t, right? T is the unit tangent vector on C. And if you remember from way, way back in chapter 12, I had mentioned that the dot product basically measures how aligned two vectors are as long as they're like unit vectors. So what this means is that the closer the direction of v is to the direction of t, the larger the value of the dot product. So in other words, the more aligned the vector field is with, right, your vector field with the curve, the larger the dot product. So that's essentially what this is doing. So how do we define circulation? Well, circulation is the measure of the tendency of a fluid to move around a curve C under a vector field V. That's the tendency. That's what circulation is. And how do we compute it? We compute it using a line integral, this line integral right here. So that's what circulation is. It's literally just measuring like how likely, or what is the tendency of a fluid to move around that curve under the forces given by this vector field V. All right, that's what circulation is. Now, here's how we're going to connect it to curl. So let P naught be a point in R3, and then let S sub A be a teeny tiny disk with radius A centered at that point P naught. So think of a very, very tiny, tiny, tiny disk, right? Very tiny radius. Then what we know is that the curl of F evaluated at a point P for any point in that disk is approximately equal to the curl of F evaluated at its center. And the approximation is an important part here. And the reason we can do this is because the curl vector is continuous. That curl function is a continuous function. But basically what we're doing is we're saying, hey, if you pick your radius to be tiny enough, then the curl of F at any point on that little tiny disk is about the same as the curl of F at the center, roughly speaking, right? So now we can use Stokes theorem, we can apply it here, and what we'll get is we'll get the following approximation to the circulation of, I'm sorry, the circulation around the boundary circle partial S sub A. So here we go. This is Stokes theorem right here. So Stokes theorem says if you want to compute this line integral, you could instead compute this surface integral, right? And just rewriting this in terms of ds here, we get that. And now that approximation says, hey, if you want to approximate this, then you could instead use the curl at that center of the disk, right? And take your unit normal vector at that point that is the center of the disk. So this is where the approximation is coming in. Now here's what's clever about this. These are constants. These are constants, and they don't depend on S. they're just, it's a dot product, right? So this is just a scalar. This is a scalar multiple, and because of that, we can pull it out of the double integral like so. And then now all we're doing is we're computing this double integral. Well, this is just literally the surface area of your surface, right? Like so. There it is. So putting all this together, actually I have that on the next slide, don't I? Yeah. Putting all this together, we have this approximation. This line integral is approximately equal to this value here multiplied by the area of the surface. And this approximation makes sense if you think about the pieces and like look at the pieces of this result, right? So the dot product here is telling you the amount of microscopic circulation, quote unquote, at the point P naught. It's basically what it's doing, right? And then we're going to scale that value by the area of the teeny tiny disk that has P naught as its center. And that's going to give us an approximation to the circulation around that teeny tiny disk. That's the basic idea. And because we're talking about teeny tiny disks, the approximation gets better as the radius of the disk goes to 0. So the smaller the disk, the better this approximation. So I hope that makes sense. Now, because this is non-zero, as long as your radius is not 0, you can divide by the area of the disk, and you get this result. And then what we get is that the curl of v at that point, dotted with the normal vector at that point, is equal to this limit as the radius of the disk goes to 0. So that's what it's really doing. Yeah, so this is the point I want to make right here. This limit gives the explicit connection between the curl of a vector field at a point and the circulation of a vector field around a closed curve. So this is kind of a connection between the microscopic and the macroscopic circulation. This is where that connection is made, that bridge through this limit. Another thing I want to point out here is that, wait, hold on one second. Let me double check. Hmm. Hmm. Yeah, actually, I'll just leave it at that. I won't make it more complicated. There you go. Okay, so this is the connection between curl and circulation. Now let's talk a little bit about curl and conservation. We're actually going to go back and prove a statement or prove a theorem that we stated back in section 16.5. Sorry, that should say 16 or section. There you go, section 16.5, and it was this one. If F is a vector field defined on a simply connected region, for example, R3, where the curl of F is 0, and whose component functions are C1, then F must be a conservative vector field. So now we're basically saying that we can prove that if the curl of F is 0, then F must be conservative, and we're going to use Stokes theorem to prove it in one line. Here we go. Okay, so from our previous work back in section 16.3, I believe, we know that if the line integral around any closed path C is equal to 0, then F is a conservative vector field. So that's basically what we're going to show at this point. So let's say we're given a closed path C, and suppose that we can find an orientable surface S whose boundary is C. We are actually able to do this, but like the book mentions as well, the proof requires advanced techniques. So we're not going to prove that we can find such a surface. We're just going to assume that we can. Math majors, you will go into those details later in a later analysis course. All right. So because we now have this surface S that has C as its boundary curve, Stokes' theorem gives us this result right here. But because the curl of F is 0, right? That means that this is the 0 vector, and so now we're integrating the 0 vector, and we're going to get 0 as the result. That's it. So now we've shown that this line integral is equal to 0 as long as you have a closed path C, a simple closed path. Now, if the curve C is not a simple path, meaning it kind of intersects itself, then what you can do is you can actually decompose it into a finite union of simple curves. So if you have, oops, if you have something like this, you can split it down the middle and do this curve and this curve separately, and then apply this result to each one of those pieces, right? So apply that to each one of those pieces, and then add up all of the integrals by finite additivity. And then since we know that the integral around any closed path is 0, that means this is 0, and thus f is conservative. And that's it. That's it. So Stokes' theorem is very nice. Very, very nice. It lets you pass between path integrals and surface integrals and back and forth, and you get flexibility. You get to kind of choose. All right, so guess what? That's it. It's time to play. Like I said, a relatively short lecture. It's a powerful theorem. I hope you enjoy it. We're going to see another very powerful theorem in the next lecture when we talk about the divergence theorem, which is also kind of like the fundamental theorem of calculus part 2 also. But I'll leave it at that, and then I will see you next time. Thank you again for listening and watching.